Hello students, welcome to EPG Pathshala. I am Professor Panchapakeshan from University of Delhi. Today you are going to discuss about the module higher order interactions, landmarks, Bose-Einstein statistics on the way to quantum field theory from the paper Radiation Theory of the physics course. After studying this module, you should be able to understand the value of higher order interactions like spin, quadrupole and magnetic dipole and how to estimate them. You should learn to estimate the power by which each order of perturbation decreases. You would have learned the derivation of Planck's law from QED with hermiticity playing a crucial role. You will learn about the landmarks, two landmarks before quantum theory of radiation, Planck's law derivation by Einstein in the year 1917, in which he first identified the spontaneous emission process, and the derivation by Satyendranath Bose in 1924, which led to the Bose-Einstein statistics. You will be able to understand that the principle of detail balance used by Einstein is a consequence of hermiticity of the Hamiltonian used in quantum mechanics. The interaction due to the magnetic moment of the electron, not included in our interaction Hamiltonian earlier so far, is next studied and shown to be of higher order and hence smaller by 1,000 times in the amplitude. The momentum k of photon in k vector dot x vector is of the order of -1 by lambda, the wavelength, and x is limited to the integral over the radius of the atom. You can call it a. The amplitude is smaller by kx modulus, and the transition probability is smaller by a factor of 10 raised to the power -3 squared, namely 10 raised to the power -6 in the magnitude, where alpha is the radius of the atom and lambda is the wavelength of the light emitted. We shall study this in section 3. Sometime the first term 1 in the expansion of the plane wave leading to dipole emission or absorption is forbidden by selection rules. The next term in the expansion then leads to the quadrupole and the magnetic dipole terms. These are the higher order terms and hence they are smaller as seen above. In studying them, it is convenient to expand the plane wave part exponential ikx in terms of spherical Bessel function and Legendre polynomials. We do this in section 4. We can apply our results obtained to calculate Planck's law for blackbody radiation, the law which started off the quantum revolution and brought Planck's constant h cross or h into physics. We make use of the hermiticity of the interaction Hamiltonian in doing this. A charged particle like electron emits radiation as well as absorbs electromagnetic radiation. So in deriving Planck's law inside a black body, one can consider a system of atoms in thermodynamic equilibrium. The emission and absorption of photons, in emitting and absorbing photons, the electrons of the atoms can be treated non-relativistically. The atom in a state A emits a photon of energy omega and goes to the state B. The atom in the state A absorbs a photon of energy omega and goes to the state B. By treating these systems of atoms in thermodynamic equilibrium, we derive the Planck's law of radiation in section 5. In section 6 and 7, we discuss two landmark works by Einstein and Satyendranath Bose. The first is Einstein's derivation of the Planck law by considering transition between two states of an atom, A and B, as mentioned earlier. Apart from two terms for absorption and emission in the presence of radiation, he had to consider a new term for spontaneous emission, even in the absence of radiation. This is the one part in the nk plus 1 part of the matrix element that we calculated. This was not known in 1917 when Einstein did his calculation. This whole derivation and Einstein's intuition is discussed in section 6. In 1924, Bose derived the Planck's law in an initially revolutionary way and a totally revolutionary way. He could not get it published, and he took the unusual step of sending the manuscript to Einstein, who, recognizing its importance, got it translated into German and got it published. Einstein also showed that it had applications to other particles than photons, which could be having a mass also, unlike photon. Photon is, of course, massless. This we know now as Bose-Einstein statistics applicable to particles of integral spin, including zero spin. Such particles are now called bosons, a name given by Dirac. Before discussing the other parts, first we will consider the higher order interactions. The first one is the spin interaction term. So far we have neglected the spin and hence the magnetic moment of the electron in its interaction with the radiation field. If you consider the spin of the electron, then we have one additional term in the interaction, Hi, which can be written as Hi spin equal to minus EH cross by 2mc sigma vector dot delta cross A. Restricting to one electron system and using the plane wave expansion of A vector, we have the following expression. Before I go to that, let me briefly explain this equation 3.1. It is really a term which involves the spin sigma dotted with the electromagnetic field. The electromagnetic field is curl of A, so it is sigma vector into curl of A, which is divergence cross A. We have Hi spin can also be written as minus EH cross by 2mc sigma vector into curl delta vector cross epsilon lambda prime vector divided by twice omega k prime multiplied by the volume. The volume will come in if you are going to discrete states. And a k prime lambda exponential minus I k prime dot x vector and a dagger k prime with exponential plus I k prime dot x vector. This simplifies to minus EH cross by 2mc into minus I by square root of V, summation over k prime and lambda prime, sigma vector dot k lambda prime vector cross epsilon vector divided by twice omega k, a k prime exponential minus I k prime dot x vector, a dagger k prime exponential plus I k prime dot x prime. For spontaneous emission of a photon process, only a dagger k prime will contribute. And thus for the process A going to B plus gamma or B plus photon, we have the matrix element of Hi spin between B omega k epsilon lambda vector in the final state and A in the initial state. So this is equal to I EH cross matrix element of between B and A of sigma vector dot k vector cross epsilon lambda into exponential minus I k vector x vector divided by 2mc square root of 2 omega k and square root of V. The corresponding first order dipole approximation interaction term is B omega k epsilon lambda Hi and A, this is a matrix element, equal to E by M B P vector dot epsilon lambda and then ket of A divided by M twice omega k V. Here we have put H cross and C equal to 1. So comparing the two, we have Hi spin by Hi is equal to E by 2m sigma vector dot k vector cross epsilon divided by E by m p vector dot epsilon lambda vector. Here k vector and p vector are momentum of photon and electron. As the typical wavelength lambda of the photons is of the order of 10 raised to minus 5 centimeters and the electron has the range of 10 raised to minus 8 centimeters, so we have k of the order of 1 over lambda photon and p is of the order of 1 by r atom. Thus Hi spin by Hi is equal to r radius of the atom divided by the wavelength of the photons. That is 10 raised to minus 8 by 10 raised to minus 5 in centimeters. This is equal to 10 raised to minus 3, which is much less than 1. Thus we see that the spin term is much smaller than the first order dipole term. The next higher order term that we consider is of magnetic dipole and quadrupole transitions. Occasionally we may have X vector matrix element between B and A equal to 0 for every state B with energy lower than that of the state A. This may be due to selection rules. In these cases, we then go back to the plane wave expansion and use the second term ik vector dot x vector in the equation 4.1. We retain the first order term. We then have to deal with the matrix element between B and A of k vector dot x vector and p vector dot epsilon lambda vector. This can be rewritten as a combination of electric quadrupole and magnetic dipole M1. We write k vector dot x vector into p vector dot epsilon lambda as ki xi pj epsilon lambda j, which is equal to half of ki epsilon lambda j multiplied by xi pj minus pi xj plus half of ki epsilon j lambda into xi pj plus pi xi. We have really subtracted the pi xi term from both the terms. Using the relation xi pj minus pi xj is equal to the angular momentum epsilon ijk lk, where L vector is x vector cross p vector is the angular momentum of the electron. We have from equation 4.2 ki xi pj epsilon lambda is equal to half k vector into epsilon lambda vector k component into lk plus half ki epsilon j into xi pj plus pi xj. The first term of equation 4.3 has k vector cross epsilon lambda vector, which is the first term in the expansion of curl A and hence denotes the magnetic field B. L is related to the angular momentum and hence can be expressed in terms of the magnetic moment mu also. The first term becomes half k vector cross epsilon lambda vector dot x vector cross p vector, which is equal to half b vector into mu vector into 2m by e, where mu vector is the magnetic moment of the electron. Thus 4.4 is the interaction of the magnetic moment of the charged particle with the magnetic field B. This term is therefore called the M1 or the magnetic dipole term. The second term of equation 4.3 is called E2 or electric quadrupole term. To simplify this term, we now use the relation commutator of p vector squared with x vector is given by minus 2i p vector, or twice m into commutator of h0 and x vector is equal to minus 2i p vector. We had used this relation in the earlier modules also, you may remember, where h0 is the free Hamiltonian. Thus p vector is equal to im h0 x vector. Using this last equation, we write the second term of equation 4.3 as ki epsilon j lambda xi pj plus pi xj is equal to im ki epsilon j into xi into commutator of h0 and xj plus commutator of h0 and xi with xj. And this gives us im ki epsilon j into xi h0 xj xi xj h0 plus H naught Xi Xj minus Xi H naught Xj. Therefore, the matrix element between B and A of Ki epsilon lambda by 2 Xi Pj plus Pi Xj is given by half into I m Ki epsilon j multiplied by minus Ea plus Eb, matrix element between B and A of Xi Xj. This is equal to half Im into minus omega into Ki Ej, matrix element of Xi Xj between B and A. This term gives rise to the electric quadrupole or the E2 term. To see this in another way, we go back to another expansion for plane wave. The other expansion for plane wave, we can write exponential I k vector dot x vector as summation over L of 2L plus 1 I to the power L JLKR, this is the spherical Bessel function, into PL cosine theta, that is the Legendre function, where theta is the angle between K and X, JLKR is a spherical Bessel function, and PL cos theta is the Legendre function. As JLKA is proportional to Ka raised to the power L for Ka much less than 1, both equation 4.1 and 4.7 have their nth term proportional to Ka raised to the power n minus 1. We are dealing with L equal to 1 term. Along with the P dot x term, this will give a product of two L equal to 1 terms. The resulting term will have L equal to 2, 1 or 0. The quadrupole term is the one with L equal to 2. This results in emission of the quadrupole term E2. We next go on, after discussing the quadrupole term and the dipole M1 dipole term, we then go on to the derivation of the Planck's law from field theory. Consider a system of atoms in thermodynamic equilibrium. The atom in a state A emits a photon of energy omega and goes to state B. The atom in state A absorbs a photon of energy and goes to state B. The processes are A goes to B plus gamma goes to A, or A goes to B plus gamma or B plus gamma goes to A, written in one form. Let EA be the energy of the atom A, EB be that of the atom B. Then EA is equal to EB plus omega. Let the population number of atoms in state A be capital N as a function of A, and state B capital N as a function of B. The transition probability for the state to go from the initial I to the final state F, omega IF, is given by the golden rule, which was derived in module 6, which for a transition is omega I going to F is equal to 2 pi into HFI, that is the matrix element, mod square, and delta function of the energy, namely EA minus EB minus omega. In the above expression, HFI is the matrix element of the interaction Hamiltonian, that is, perturbation theory is assumed to be valid. In the equilibrium state, NB by NA, that is the number of atoms in the state B divided by the number of atoms in the state A, is equal to exponential minus IEB over KBT, where KB is the Boltzmann constant, divided by exponential minus EA divided by KBT, which is equal to exponential omega by KBT. And NB into the transition probability for the state B to go to gamma A is equal to NA into the transition probability for E to go to B plus gamma in the equilibrium situation. In the above, KB is the Boltzmann constant, as I explained, and T is the equilibrium temperature. If E lambda is the polarization vector of the photon of energy omega and momentum k, then omega transition probability for A going to B plus gamma divided by transition probability for B plus gamma going to A is given by nk lambda plus 1 divided by nk into the summation of the matrix element square of exponential minus ikx into epsilon dot p divided by the same quantity matrix element for exponential plus ikx into epsilon lambda into p, given in equation 5.5. It is easily seen that the matrix element between b and a of exponential minus ikx p dot epsilon is equal to a, the matrix element which is the conjugate, namely the matrix element of p dot epsilon into exponential plus ikx between the states A and B. That is, A is the bra and B is the sket. The whole thing is complex conjugated. So that is equal to exponential ikx into p dot epsilon between the states A and B, the complex conjugate of that. This is due to hermiticity of the Hamiltonian used for interaction. So using this relation, the number in the state B divided by the number in state A, which is exponential omega by kBt, becomes equal to nk lambda plus 1 divided by nk lambda. Or nk lambda has a very interesting expression, 1 divided by exponential omega by kBt minus 1. This is equation 5.7. All this is for the photon states which satisfy omega equal to Ea minus Eb. The number of states dn in a black body filled with radiation is obtained using the same arguments as for density of states rho omega and is V into 2 into 4 pi omega squared d omega divided by 2 pi cubed, which is equal to 8 pi omega squared d omega capital V divided by 2 pi cubed. The factor 2 is due to the availability of two possible directions in which light can be polarized. Thus, the number of photons with an energy from omega and omega plus d omega in the volume V is dn at the energy omega, which is equal to dn divided by exponential omega by kBt minus 1, which is equal to 8 pi omega squared d omega capital V divided by 2 pi cubed into exponential omega kBt minus 1. The density of radiant energy in the frequency range from omega and omega plus d omega is d capital N of omega, which is equal to dn divided by exponential omega kBt minus 1, which is equal to 8 pi omega squared dWV into 2 pi cubed into minus 1. The density of radiant energy in the frequency range between omega and d plus omega, therefore, is u of omega t d omega into, which is equal to omega into dn omega divided by v into 8 pi omega cubed d omega into 2 pi cubed exponential omega kBt minus 1, which is equal to omega cubed d omega divided by pi squared into exponential omega kBt minus 1. As omega is 2 pi nu, h cross is 1 and c equal to 1, we have h cross is equal to 2 pi and the u nu t d nu is equal to 16 pi squared nu cubed d nu divided by exponential 2 pi nu by kBt minus 1, which is really the Planck's radiation law for determining the energy density u as a function of omega and t, or u as a function of nu and t of black body radiation. Einstein derivation of Planck's law in spontaneous emission. The derivation given by Einstein in 1917, when he first identified the factor for spontaneous emission, will also be briefly mentioned now. Of course, the field theory derivation we given just above could happen only after 1927, but Einstein derived this formula in his own way, in an intuitive way, in 1917. Let the initial state of electron be n with energy En. After absorbing a photon, it goes to the state m. Therefore, Em equals En plus omega. Let the population numbers in the state m and n be n subscript m, n subscript n respectively. Einstein realized that the probability per unit time per atom for emission transition must have two parts. We denote the spontaneous emission by A, which does not need any radiation to be present, and the stimulated emission by capital B into epsilon omega, which is proportional to the amount of radiation present. The absorbed emission is denoted by B prime epsilon of omega and depends on the radiation present. In thermodynamic equilibrium, we have n for the energy n and B prime epsilon omega and n for the state m, multiplied by A plus B epsilon of omega. Also, the absorbed emission is denoted by B prime into epsilon and depends on the radiation present. In thermodynamic equilibrium, these must be equal. So, Nn into B prime into epsilon is equal to Nm into A plus B epsilon of omega. Or Nm over Nn, which is equal to exponential minus Em by kT divided by exponential minus En by kT is equal to exponential minus Em minus En divided by kT. From 6.2 and 6.3, we get B prime epsilon nu over A plus B epsilon is equal to exponential minus omega by kT. Or exponential omega by kT is equal to B over B prime plus A over B prime epsilon. Or B over B prime into exponential omega by kT is equal to 1 plus A over B epsilon. Or epsilon omega is equal to A by B divided by B prime into exponential omega kT minus 1. Einstein argued that from the principle of detailed balance, B prime is equal to B. To derive the law from field theory, we had used hermiticity of the Hamiltonian. Comparing 6.5 with Planck's law 5.10, we get A is equal to B into omega cubed by pi squared. Einstein's derivation was the first time that the whole idea of spontaneous emission was identified by him and was used in deriving the Planck's law. Bose's derivation of Planck's law. Using statistical mechanics, Bose calculated the probability for distributing n photons over Gi cells, all having energy epsilon I. Since there can be any number of photons in one cell, this corresponds to inserting Gi minus 1 partitions between Ni photons. If we have Gi equal to 4, we have, as shown in the picture, 3 partitions separating them. These are partitions G1, G2 and G3. They are separating the dots, showing the dots are photons and the vertical lines are partitions, G1, G2 and G3. The probability for the distribution is then given by capital W, which is a product of Ni plus Gi minus 1 divided by Ni factorial and Gi minus 1 factorial. This has to be maximized with the constraint that the total energy capital E sum over Ni into epsilon I is constant. Using the Lagrange method of multipliers, we can calculate that Ni is equal to Gi divided by exponential beta epsilon t minus 1, where beta is a multiplier. Bose calculated the number of states per unit volume available for the photon by considering the photons to be particles and using the expression we used earlier for rho omega, or the density of states. Rho omega is equal to 2 into 4 pi into omega squared divided by h cubed, which is equal to 8 pi omega cube divided by 2 pi h cross whole cubed, which is equal to omega squared divided by pi squared. Taking number of levels for one energy Gi equal to 1 and multiplying by energy of each photon omega, we get UW, or the density of radiation with omega, energy omega, into dW equal to omega cube d omega divided by exponential beta omega minus 1 multiplied by pi squared in the denominator. Bose's paper was rejected by a journal for publication. So he sent it in 1924 to Professor Einstein, requesting him to forward it for publication if he thought it was correct. Einstein translated the paper into German language and sent it for publication, and wrote a few more papers applying the Bose method of counting to normal gases or particles with masses. This was the birth of systems obeying Bose-Einstein statistics. We now know that integral including zero spin particles obey Bose statistics and are called bosons. We saw in the earlier module that bosons, scalar particles, satisfy commutation relations when quantized. Photons have spin 1 and so are bosons. They do not have 2s plus 1 or 3 components, but have only 2 components or polarizations, as they have zero mass. Every zero mass implies gauge constraints, and as we have seen for the case of the photon, how gauge constraints reduce the degrees of freedom to just 2 polarizations. We have also discussed the derivation of Planck's law by Satyen Bose, S.N. Bose. There was criticism that the counting of states by Bose and Einstein violated the independent nature of particles. Einstein accepted this criticism, but said that the result was anyway right, and they have to find out the reason for the mysterious attraction between the photons. We now know that the symmetry of boson wave function brings in an attraction just as that of antisymmetry of fermions, that is, particles with half-integral spin, brings in a repulsion leading to the Pauli principle. This was finally explained by P.A.M. Dirac in 1926. The statistics obeyed by fermions is called Fermi-Dirac statistics, and the statistics obeyed by the Bose-Einstein theory, which we discussed earlier, is now called the Bose-Einstein statistics. Planck introduced the photon in 1900, and Einstein gave the photoelectric effect in 1905. But even in 1924, photon was still not accepted as a particle, and Einstein expressed surprise at the way Bose had derived the number of states rho omega. It took a long time, 27 years, for dual nature of light to be accepted. Abraham Pais, in his book on Einstein and his work, mentions 4 path-breaking papers published before quantum revolution in 1926. They are, first one by Max Planck in 1900, then on photoelectric effect by Albert Einstein in 1905, and then Bohr's derivation of the energy levels in 1911, and that of Satyendranath Bose in 1924, deriving the Planck's law. In this module, we have studied the higher order interactions like spin interaction, magnetic quadrupole, magnetic dipole, and electric quadrupole interactions. We find these higher order terms are 1,000 times smaller as they are proportional to the ratio of the radius of the atom to the wavelength of light. We have learnt how Planck's law can be derived from quantum field theory. We have also learnt how Einstein derived the Planck's law from Bohr's theory in 1917, and Satyendranath Bose derived it from statistical arguments in 1924 before the discovery of quantum mechanics. In 1926, quantum mechanics was discovered, and Bose became the first author on quantum statistics.